right? So there's actually a very practical application of that, of this, what I'm talking about, and that is Le Chatelier's principle. So this is actually extremely useful for any reversible reaction, and that is to figure out what's going to happen. Is it going to shift forward or shift backward whenever I stress a system? So again, this is not in the textbook, so I provided a supplemental link if you need to go see it. All right, so Le Chatelier's principle is actually very simple. It is for an equilibrium system, okay? If I stress it, so if an equilibrium system is stressed, and I'll talk about what that means in a minute. If it's stressed, it is going to shift. It will shift. It'll either go forward or backward. Okay, so go forward, backward, reaction-wise. It'll shift that way to essentially relieve the stress, or get back to equilibrium. Okay, so re-establish equilibrium. Okay, so if you stress a system, it's going to want to shift in order to counteract kind of that stress. Meaning if I add a bunch of stuff in, it's going to have to shift to counteract that stress. And it acts very much like a balance. That's why I have a picture of a balance here. If I put something in, it's going to have to even back out. So I'm going to show you how to figure out how that happens. So practical use is in the Haber process, and this is how we make ammonia for fertilizer. Extremely important process. It's very favorable in creating ammonia at high pressures and high temperatures. So you can see at the highest temperature and highest pressure here, I'm actually producing more ammonia. So that's for this specific reaction. That's not for every reversible reaction. We're going to talk about why it works this way. Okay. So I want, and this is the Haber process, right? I want N2 nitrogen and hydrogen, and I want to make it to ammonia. And this is a reversible process. And if I balance this, it looks like that. Essentially, I am trying to make this. So I want to shift it forward. I want to make more ammonia, make more ammonia. So what stresses can I do to actually cause it to shift that way? All right. So the three types of stresses are concentration, pressure, and temperature. So I can stress a system by adding or removing reactants or products. Okay, now when you have a system going, it's really easy to add stuff in. But if you're removing something, actually you can get it to like react in a different reaction, or if you have some way to remove it, you can do that. So changing the concentration affects the equilibrium. Changing the pressure, and this is usually done by changing the size of the container. So if I make it into a smaller container, it's going to have a higher pressure. Okay, so changing volume. Or changing the temperature, of course, heating or cooling the reaction. Okay, if you heat it up, is it going to produce more products? Or if you cool it down, is it going to produce more products? And it actually depends on a couple of things. So we're going to look at all three of these. You guys are going to do a lab with these, so kind of keep these in mind. Don't shove them out of your mind just yet. So concentration-wise, and this is probably the most important one, for Le Chatelier's principle. And we're looking at the same reaction here. This is for the Haber process. So the reaction is N2 plus 3H2 makes 2NH3. Okay. And for essentially what happens in this, anytime you add a reactant, it is going to shift to the right. So again, I want you to think of it as a balance. If I add a reactant, some of it is going to have to shift and make products in order to reestablish an equilibrium. So if I add something in, it's going to have to shift to the other side in order to balance back out. Now, the same is true as if I remove something. So if I take some out of here, it's going to have to shift backward toward wherever I took that stuff out to actually reestablish the equilibrium. So if I add a reactant, it would shift right. And if I remove a reactant, it's going to shift to the left. So like if I took some N2 out of here, it's going to shift back to the left in order to actually reestablish that equilibrium, or like fill in that gap. You kind of think of it that way as well. All right, so products, if I add in a product, then it's going to have to shift to the other side to balance back out. So if you add a product, it's going to shift to the left side to balance back out. If I add in a bunch of product, it's going to have to shift back to the reactants to even out. And if I remove a product, it's going to shift right to kind of fill in that gap. So if I take out some NH3, it's going to have to shift to fill in that gap. I take some out, it's going to have to shift that way to fill it back in. Okay, so this is actually a graph of me stressing an equilibrium system. What happens? So in this specific example, I added in H2. Okay? Added in H2. So it was an equilibrium. I added in H2. So that's like adding in a reactant. You can see there's a spike there because I added it in. And then over time, you can see that after I stressed it, the H2 concentration goes down, the N2 concentration goes down, and the NH3 concentration goes up. So that would mean that I'm making more NH3 and I'm using up that N2 and H2. So what happened when I added in H2? Well, it went forward to produce more NH3 and it used up some of the N2 and H2. Right? So if you add something, it's going to shift away. And if you take something out, it is going to shift towards. So that's kind of how the whole principle works. Okay. So in the whole rebalancing, if you add something, the equilibrium will shift away. So to the other side from whatever you added. And if you remove something, it will shift toward whatever it is that you removed to kind of fill in that gap. All right, so that's how concentration works. Now we're going to talk about pressure. I want you to remember Boyle's law for a moment, and that says that pressure and volume are inversely proportional, right? If you put something in a smaller container, it's going to increase the pressure. If you give it more space, it's going to decrease the pressure. All right, and that actually affects equilibrium. So essentially, if you increase the pressure or decrease the volume, same thing, the reaction is going to want to shift because it doesn't have much space. It's going to want to try to have as few particles in there as possible. So what's going to happen is the reaction is going to shift to whichever side has less moles of gas, because the less moles you have, the less pressure there's going to be. So to relieve this pressure, when you put it in a small container, it has to shift to the side that has less moles of gas. So it wants to have as few particles as possible. Whereas if you gave it a bunch of space, it's going to want to fill that space. So if I decrease the pressure by increasing the volume or giving it more space, the reaction is going to shift to the side with more moles of gas. Okay, so if it has more space, it's going to shift in whichever way will fill that space. Okay, so to kind of check this, we're going to look at the Haber process and see if that actually matched the principle that we're talking about. So, right, this was the Haber process, and they're all gaseous. Okay, so I want you to look at this. The reactants, the total moles on the reactant side are 4 moles of gas. Okay, 1 N2 and 3 H2s. Whereas the total moles on the product side of gas are 2. So if it wants to go, it wants to shift whichever way depending on the pressure. So I want it to go to the right? I want to produce ammonia. So I want to shift it to the right. So if I want to shift it to the side that has less moles, this one only has 2 moles, I want to put it under a high pressure. So yes, this does match exactly what we said. High pressure in this specific case would shift it to the right because it has less moles of gas. So it's going to make more NH3 and make more NH3. Okay, so you need to look at the moles of gas when we're talking about pressure. Now, finally, temperature can also shift a reaction. Now we know temperature does change the K value, and that's why it will shift. The K value is going to change with temperature, and it moves either to the left or to the right based on if it's endothermic or exothermic. So, right, an endothermic reaction is reactants. Heat would be on the left side plus heat. You have to put heat in, makes the products. Whereas exothermic would be like reactants, makes products, and it gives off heat. Okay, so the heat is either a reactant or it's a product. Now you can think about this just like concentration. If I heat it up or increase the temperature, so if I increase the temperature, it's going to shift to the other side. So it's like putting something in. It's like I'm putting a reactant in. It's going to shift to the other side. So if something is endothermic, if I increase the temperature, it's going to shift right. And if I decrease the temperature, it's like taking heat out. Okay, it's going to try to fill in that gap. It's going to shift left. Okay, and same is true for exothermic. You think of heat as a product in this case. So if I increase the temperature of an exothermic reaction, that would be like adding heat in, it's going to shift away from the heat, so it's going to shift left. If I add heat in, it's going to shift to the left side. And if I decrease the temperature or cool it down, okay, that would be like taking heat out, it's going to shift to the right side to kind of fill that in. Okay, so I want to talk about this example really quick. This is the N2O4 example. Is it endothermic or exothermic? So we can tell by looking at shifts if something is endothermic or exothermic. So this shows you, and you might not be able to see it really well, but this is when it's really cold or it's frozen. So when it's cold, it's clear and it's like all N2O4. And when it's hot, it's brown and it's like almost all NO2. Okay, so if I'm looking at this reaction, N2O4 makes 2NO2, I want to figure out which side heat is on. So when I heat this up, which way did it shift? Okay, I heated it up and it turned brown. So that means it shifted to make more NO2. So if I look at the data, heat caused it to go that way. And when I cooled it down, it turned to all N2O4. When I cool it down, it all shifted to the N2O4 side. So that must mean that heat was a reactant because when I added heat, it shifted to the right. And when I removed heat, it shifted to the left. So that must mean that this is an endothermic reaction. Okay, again, something you're going to be doing when you get to your lab. Okay, so the last thing I want to talk about is kind of application of this and catalysts. So you might be thinking, well, what happens when I add a catalyst? Is it going to shift right or is it going to shift left? And actually a catalyst isn't going to shift the reaction. So, right, a catalyst decreases the activation energy. It actually speeds up both reactions because it affects, speeds up the forward and the reverse. Specifically because it lowers the activation energy, well, for the forward reaction and the reverse reaction. So if they both speed up, then it doesn't shift. It just goes faster. That's it. Okay, so catalysts are not going to shift a reaction equilibrium. Okay, so looking at this application really quick, I've been talking about ammonia production because ammonia is extremely important. This is kind of how it works. Yes, they do use a catalyst to make it go faster. Remember, we said we have to be at high temperatures and high pressures to make a lot of ammonia. So high temperatures and high pressures, right? Because if I look at the reaction, my N2 plus 3H2 makes 2NH3. We know that high temperatures cause it to produce more ammonia, so it must be endothermic. Okay. High pressures cause it to shift right because there's less moles on the right side. As this reaction happens, they remove the NH3, and as you take more out, that's going to cause it to shift right. So all of these things cause a rightward shift in this reaction to produce more and more and more ammonia. And a catalyst is just going to make it go faster, right? Why is this important? Well, over 100 million tons are produced a year, which actually uses 1 to 2% of the annual world's energy supply, which is a lot if you think about it, okay? It uses an insane amount of energy, but ammonia is extremely important to drive agriculture so we have things to eat. So that's why I talk about the Haber process. It's a really great example for what we're talking about. Okay, so you guys try number 16, try to figure out what will happen to this reaction, which way will it shift? You can just say right or left or draw an arrow when I do each of these things. All right, should get that A shifts to the right side because I added an A, so it shifts away. If I take out B, it's gonna shift toward, it's gonna shift left. If I increase the pressure, it's gonna shift right because there's only 1 mole of gas over on the right, whereas there are 3 on the left. And if I increase the temperature, it's going to shift left because it is an exothermic reaction.